One of the skills of this unit is to be able to write out complete net redox reactions. There's going to be primarily two ways. Either you need to predict reactions in where you get to use your data table, or you're going to make up your own half reactions using different techniques. For now, we are going to look at the examples when we get to use our data table. Okay, so anytime you are predicting a reaction, which means you're just given a bunch of reactants. So in this case, you have gold, you have silver, and you want to know if you can store nitric acid in one of these. Well, first thing I'm always going to do when I have to predict a reaction, okay, and now this isn't when you are given a full reaction, it's just when you're given reactants. Okay, so this will be an example just like this, where it's just a reaction, or most times when you're dealing with redox stoichiometry, which involves titration often, you'll get to first list your entities and then utilize your data table to go from there. Listing your entities is the most important step when you're predicting a reaction. You must do this correctly and carefully. Okay? When you are listing your entities, you must be certain that you're minding your states of matter and your charges. In particular, your charges. If you forget to put your charges down, you are going to end up using your data table and identifying these entities as the opposite of what they are. Okay, so please be careful with that step. Once you get this step, usually the rest of it flows pretty smooth. Okay, so first thing, we've listed our entities. Okay, now when I'm determining my entities, I have to decide which substances are going to break up, which will not. So here we had pure gold, we had pure silver. Those aren't going to break up. No pure element will break up. But then I have this H and then an NO3. Well, that came from nitric acid. Any strong acid, which they will be in this unit all the time, or soluble ionic compounds, will break up. Now, your strong bases would fall into that category of soluble ionic compounds. Okay. Everything else, pure elements, molecular compounds, polyatomic ions like NO3, notice we're not breaking that down any further. Okay. All these other substances do not. Only acids and soluble ionic compounds will break up. Now, once you've taken care of that, then we're going to go ahead and use my data table to determine everything as being an OA or an RA. Turn on the lamp here. You can see this data table a little better. Well, that's a bit dark. However, basically what you need to do is just find each of these entities. So one of my entities was gold, pure gold. It's on the right-hand side. Well, that means it's a reducing agent. And if you may recall, anytime you have a pure metal, that's going to be a reducing agent. So I want to save yourself some time. You see a pure metal, identify it that way. You don't even need your data table a lot of the time. RA, RA. We also determined prior to this that water is on both sides. Now, that being said, water comes into play quite a bit. Okay, here it is as a reducing agent, and here it is as an oxidizing agent. Okay, very weak oxidizing agent because it's way down here on the left. Very weak reducing agent because it's way up on the right-hand side. Now, H plus is an oxidizing agent. It's a positive ion. They'll always be oxidizing agents. But H plus you see a lot, okay, especially in the upper left-hand side. Okay, it's in this half reaction, this one, and this one, here, and here. Lots of places. So we need to find it as we have represented it as part of our entities. And so we have H plus here all by itself. Okay, that's your reference reduction potential of hydrogen. But then, do I have it anywhere else? If you look up here, here's the NO3. Okay, I have NO3 ions, I have H ions, so I can confidently link those two guys together, and as one, they are an oxidizing agent. If the H plus was not there, then NO3 would not be considered an oxidizing agent, it'd just be a spectator. You have, when you're identifying as OAs and RAs, they must be exactly as the way you have them listed. Okay, so then from there, we look at determining the SOA and the SRA. So the SOAs that we, or the OAs, sorry, that we have are water, right here, and H plus, and HNO3. Well, the HNO3 is the highest up on the left, which makes it our strongest oxidizing agent. And for our reducing agents, we have gold, we have pure water, and then we have silver. Silver is the farthest down on the right-hand side, so therefore it's my reducing agent. Or my strongest reducing agent, sorry. So that means that's my SRA, and the combination of H and NO3 is my strongest oxidizing agents. Okay? Alright, so next step, step 4, determine spontaneity. Spontaneity rule is pretty simple. Basically, once you find your strongest oxidizing agent, which we determined to be HNO3 right here, we look at the physical position of the SOA versus the SRA. We can see here the SOA is above the SRA. That means the reaction is spontaneous. Okay? Therefore, HNO3 and silver would react, so you wouldn't store your nitric acid in silver. Whereas gold, very weak reducing agent, is above the HNO3. Since if the reducing agent is above the oxidizing agent, it is non-spontaneous, which means the reaction will not occur. So we've determined that the reaction is in fact spontaneous, so we're going to write up the half reactions from the redox table and carry on. So, my oxidizing agent. I'm going to write it out exactly as it's listed in the table. I just copied that word for word. Strong reducing agent, all I need to do is reverse it. Notice that this is exact opposite of what was in your redox table. Okay, and the reason I have to do that is because I need to have two half reactions, one of which is showing a gain of electrons, one of which is showing a loss of electrons. Okay, so now I have two half reactions. Well, in all redox, electrons gained must equal electrons lost. Well, in this one I have a gain of 2 and loss of 1, which means I have to multiply this whole half reaction by a factor of 2. Okay, and that's going to balance out our electrons, and then we can get our net reaction. And to do that, I cancel out my electrons because they end up being the same. I have 2 NO3s left, 4 H pluses, 2 silver, because I multiplied this by a factor of 2. Those are all my reactants. Produce 2 silver ions, one of these N2O4s, and 2 waters. And then I'm left with my net reaction. Make sure when you do this, you do not have any electrons left in your net. If you do, you screwed up somewhere.